Welcome back, everybody. So let's continue. So first, who already has first-hand experience of the postcard thing? Who has already been sitting at a table preparing postcards like this? Some of you, right? Maybe for weddings, typically. Anyway, what we learn here is that the number of groups that takes care of the tasks need not be the same as the number of tasks. Here, we have 3 groups and 5 tasks. That's what we learn in here, right? So each one of these groups is called a map slot or a reduce slot, right? And each one of the tasks is called a map task or a reduce task. So this is the one message here. And you see why it's not the same number. It's because they might not have the same speed. So by having more tasks, let's say 3 or 5 times the number of tasks compared to the number of groups, then you're giving the opportunity to the very efficient groups to handle more tasks, and for the slower groups to handle less tasks, and you still nicely distribute it all over, right? So this assignment of tasks to the slots is done dynamically, right? You finish, then you get the next task, right? Who is with me on that? All right, so now let's see how it's translating to concretely to MapReduce. Be careful with the terminology. Pay attention to the terminology. What we call map function is this method in Java that I showed you earlier. It's a mathematical function that takes one input key value and outputs 0, 1, or more intermediate key values. That is a map function. What we call a reduce function is again a mathematical function that takes one group of key values with the same key, and it must be all of them that have that key, one complete group of key value pairs with the same key, and that outputs 0, 1, or more output key values. Who is still with me? Right? There's nothing new in here so far. The combine function is also a mathematical function that takes a group of intermediate key values with the same key, but it doesn't need to be complete. That can be partial, as long as they have the same key. And it combines them into typically one, if you want to be efficient, one intermediate key value. It squeezes them into just one. So that's the functions. Now we have the notion of tasks. What is a map task? Well, the map task is basically the sequential calls of the map function to every key value that there is in your split. And remember, a split is an HDFS block. So we might have 100,000 key values in the HDFS block that we are reading. So we are calling 100,000 times the map function. I insist on sequential. There is no parallelism. It's a for loop, sequential. We just call it one after the other on every key value that there is in there. That's the map task. The reduce task is also a repetitive call of the reduce function. You might, just like you can have multiple key values coming from the same HDFS block, you might also have in the same reduce task multiple groups that belong to the same task. Why? Batch processing. If we had one task per key, that would be inefficient. If you have 1 million keys, you would have 1 million tasks that would take forever. So we batch process, which means that we put multiple groups in the same reduce task, and we call sequentially, it's again sequential, no parallelism. We call the reduce function sequentially on each one of the groups that belong to our task. Who is still with me? Right, very good. So these are the map tasks and the reduce task. Combine tasks do not exist. Combine is just the function. You provide the function to MapReduce, and MapReduce is free to use or not use that function when it spills and when it merges. That's all it is. There is no such thing as a combine task, right? Then we have, so that's why you basically call the combine function when you spill to disk these intermediate values that you might have written from a task, you might combine them and then reduce the size of the files that you write to disk and of the key value pairs you send over the network. All right? So that's how it fits. Then we have the notion of map slot. A map slot is not a partition. A map slot is about CPU core resources and memory resources. think of a map slot as one CPU core, virtual core eventually, because you know you can double the number of cores with hyperthreading virtually. So one virtual core gives you one map slot, one thread. What does a map slot do? It just takes tasks one by one. It grabs the task, and when it's done with the first task, calling sequentially the map function, it grabs the second task, if there is still one available in the queue, then calls the map function sequentially. Then there's a third task, calls the map function sequentially, and so on. This is all sequential. First task, then the second task, then the third task, and at some point you run out of tasks because everything is done, and you just patiently wait until everybody else is done. Who is with me? Right, very good. And basically you need to imagine that as a result of that task, either it fits in memory, then it's in memory, or that resulted in spilled files over the disk, and eventually when you merge it, a single merge intermediate file. This results again, spill, then merge, and you get again one more intermediate file. And again, this you get one more intermediate file. So in here we got 3 intermediate files that contain key values, the intermediate key values, sorted by key, not necessarily by value. The value, it doesn't bother. You can, if you want, that's called secondary sorting. You can require it to also sort the values, but otherwise it's not going to bother sorting the values within the same key, right? Okay, so who is with me on this? Right, so a slot, which is a CPU core, grabs the tasks one by one and calls repeatedly the map function plenty of times within each task, then the next task, then the next task, then the next task, right? It's like the people with the postcards. But now you're going to tell me what's the purpose of MapReduce if everything is sequential, right? So where does the parallelism happen? Well, it happens because we don't have just one CPU core. We might have 1,000 machines with each 16 cores. So it means that we have plenty of slots that run in parallel. Right. So I will show you that. Just before I move on, the same thing with the reduced slots. The reduced slots are also CPU cores, and the CPU cores are also taking over reduced tasks one after the other. And then every time for every one of these tasks, that outputs one file to HDFS, one file to HDFS, one file to HDFS. Right? So this is part 1, part 2, part 3. This is what I told you about, right? When they write to the output directory. Who is with me? Very good. Okay, and so now you have to imagine, if you think about the sorting question that was asked, this reduced slot right here that is processing reduced task number 1 is going to connect to each one of the 1,000 map slots requesting the key values that they have, and they might come from everywhere in the cluster, right? So maybe this came from machine 5, this came from machine 42, and this came from machine 100, right? They might come from different machines. So you get them all, and then it's going to group them once it have received them again by key here, here, and here. Again, the values are not necessarily sorted right here. It can really be a mess unless the user requires a secondary sorting of the values. They are not going to be sorted. Okay. Okay, so this is the reduce slot that is evaluating or taking care of multiple reduce tasks, one after the other, and finally writes for every reduce task one HDFS file, parts N, on the disk. Combine slot does not exist. The combine is just a function you provide when you split and merge, that's all. So there's no such thing as a combine slot. And finally, the map face. The map face consists of all the virtual CPU cores we have all over the cluster, and we can be talking about thousands of them, multiple per machine. Maybe we have 16 slots per machine times 1,000 machines, that's 16,000 slots. Every slot is taking care of its tasks. The fast ones might have more tasks. The slow ones may take forever and process less tasks. It's all dynamic. And when you run out of tasks, you are idle until everybody is done. Right? This is where we get the parallelism. is because we spread the tasks all over the CPU cores. Who is with me? Right, very good. And again, for the reduce slot, it's the same thing. We have them spread all over the cluster. It's the CPU cores, and they just take the reduce task one by one. Just for your visuals in your mind, typically the number of reduced tasks is going to be a bit less than the number of map tasks, right? So it really depends, of course, on the specifics of your job. Just to give you an order of magnitude. The number of map tasks, that's basically the number of HDFS blocks by default, if you take a task to be an HDFS block. So it's whatever the size of your data is, the number of blocks that's giving you the tasks. That typically you don't have a choice on, that's what your data is. Ideally, you should pick a number of map slots that is less than the number of tasks, maybe by a factor of 3 or 5. Let's say it can vary, of course, that you can play around with these things, but 3 or 5 times tasks, 3 or 5 times more than the number of slots is kind of well to distribute a bit over the cluster.
Here is a question on Zoom.
Yes?
Why would we want to sort the values before calling the reduce function? Is this for things like median where order matters?
Let me see. Is it on Zoom or I don't see any? Oh, that's private to you. Yeah.
So why would we want to sort the values before calling the reduce function?
So you're talking about the secondary sort, right? What I call the secondary sort, which is optional.
I guess so.
Right. So that's basically when the user explicitly wants to sort the values. Well, there are people who might be advanced users of MapReduce and who knows about how to tweak things, who would like some more guarantees in the ordering of the values that are produced by MapReduce at the end. Maybe they want to specifically sort data. So if their goal is to sort data, then these people might want to also have the intermediate values sorted in such a way that they get some good guarantees at the end. If you want to go in that direction, though, and this is why I'm talking about advanced users, is that the keys are sorted within each map task, right? So when you output them, you might want to sort them so that it makes it more efficient to distribute them during the shuffling. But the distribution of the keys to the reduced tasks is through a hash. So there's no ordering at all in there, right? It's just going all around the cluster. So an advanced user that would like to tweak things and also get an ordering of the keys might need to overwrite or create their own partitioning mechanism. They would need to find where the hash function is and so on, where the partitioner is, and overwrite it with their own code or in order to change the way things are partitioned. And maybe they will partition by intervals instead of using a hash, right? And of course, partitioning by intervals requires advanced knowledge of the data. You can only do that if you know the data and you know more or less how it distributes. So an advanced user might do that. So you see the advanced engineers might be able to get more out of MapReduce and to get some sorting guarantees at the end. But it's complex. The standard user of MapReduce is not going to tweak these things. The values don't have an order guarantee, and the keys that you get in the output might also not have an order guarantee, right? Does it answer your question? We'll get to you.
Yes, it makes a lot of sense.
All right.
There's a question over here.
For the reduce part, how are the tasks assigned? Are they assigned before any task is done, or is it just a queue?
So you're asking how are the intermediate values assigned to the reduced task, or how are the reduced tasks assigned to the reduced slots?
No, how are the reduced task assigned to the reduced slot?
Oh, first come, first serve. Okay, the tasks are there, basically, it's hashed. So you decide before the job, you decide how many tasks you have. That's a parameter that you configure. You say, I want 10 tasks or 20 tasks or 100 tasks. Then you have the number of slots that you can also configure. And then the slots are just taking whatever task is in there, right? So you might have, let's say, to simplify, you have twice as many tasks as slots for the reduced side. So it means every slot will roughly have 2 tasks. Some might have 3, some might have 1. So basically, it means that they are just going to grab each one a task, And then whoever is done grabs the next task, right? Until there are no more tasks. So there's a bit of undeterminism in there. It's whoever grabs their task first, right? The factor between reduced task and reduced slots, I have no idea how they came up with these numbers, but there are two magic numbers. I think the first magic number is 0.95 and the second magic number is 1.75. I have no idea how they computed that, but apparently that's the factor you should use when you configure your reduced task and your reduced slots. 0.95 basically means you have slightly less reduced tasks than reduced slots. That basically means you spread it all over the cluster with one slot with every task, but you still have a few more resources left just in case something goes wrong. And 1.75 means you have slightly less than two more. So that's also allowing you to spread it a little bit over the cluster, but without pushing it too much. So 0.95, 1.75. These are the two magic numbers that engineers use in practice to configure. Right. So that wasn't part of your question, but does it help?
Yep.
Yeah. Okay. Any more questions? Yes, over there.
Dimo.
Well, luckily, it's made of some soft materials, so it can fall without any problem. Yeah, go ahead.
So data locality doesn't play a role in the reduce task allocation?
Nope, only for the map phase. Yeah, on the map phase, you read locally, but when you reduce, it's just shuffled anyway. Yeah.
When assigning tasks in the map phase, how exactly do we take account data locality?
In the map phase, it's just that you're going to have the data sets distributed all over the place in the cluster with the blocks all over the machines. And MapReduce is aware of that. And it's going to, when the map slots grab their next task, they will try to get a task for which the block has a local copy. When they grab the task, they will prioritize these tasks where they can read locally. And if there's none, then of course they will have a remote read and take whatever task is left. Right. So this is how it's done. You're aware of where if you have a local replica or not. Okay. Does it answer your question? Awesome. More questions? Okay. All right. So then let's move on if the clicker actually accepts. A combined slot doesn't exist. This is in parallel. And finally, we write, there's locality, by the way, when you write. When a reduced task leads to one HDFS file, there's a local write for the first replica and then a few remote writes for the other replicas. Okay? And no combined phase either. The only thing that has combined in it is the combine function. So that means that you have this function called sequentially called within a task, the task sequentially processed by the slots, and the slots correspond to virtual cores in parallel across the machines. Who is with me? Right, very good. So that's a good visual. So now you know, never say mapper, reducer, and combiner. Be very precise in the wording. So in practice, in MapReduce version 1, we statically allocate the slots. A slot is either a map slot or a reduce slot. And that does mean that during the map phase, the reduce slots are idle. They might start downloading a bit, but they are mostly idle. Okay. All right. One small tricky point I want to make you aware of when I say that a split is an HDFS block, there is actually a small difficulty to it. So a task is a map task or a reduce task, and every one of the tasks corresponds to one HDFS block in the input. So it might seem simple, right? But in fact, if you look at the details, you might remember that the HDFS blocks are bitwise. You have 128 megabytes, and then you cut the block. But the splits are based on key values. A split has an integer, a whole number of key values. Do you see the problem? The last key value might spill over into the next block. That's exactly the same thing we had in HBase when we had the key values with the H blocks in HBase, right? And that, again, has to do whether you organize your partitions at the bit level or at the record level, right? And so the HDFS blocks are at the bit level, but the splits are at the record level. What I call a record is a key value. So it means that because of this discrepancy between the two, between the splits and the blocks, when we actually read this split here, most of the key values will be in the block, but the last key value is very likely to go over and finish in the next block. So there is a little bit to read remotely if that next block is not on the same machine. There's nothing we can do about it, because in fact, to have the block exactly finish where the key value stops, you have to be lucky. So this is rather rare, right? So it's almost guaranteed the last key value will finish in the next block. So this is why in HDFS, you have a way to read not the entire block, but just the first few bytes, right? So you can ask for a partial read. That doesn't make it random access because you do it rarely. You just do it at the end for just the final bytes that you want to read, right? Who is with me on that? Right, okay. Luckily, as a user of MapReduce, you don't need to worry about that because the MapReduce engineers took care of it in Java to resolve that with a very clean implementation to do this remote read. So again, it's usually going to happen. It's very rare that that doesn't happen at all. Okay, and now to wrap up on MapReduce, I have to tell you about the developments that happened after it. Let me first give you an intuition of what we'd like. MapReduce is a low-level API. You have to come up with a map function and a reduce function. That requires a bit of imagination and figuring out what map function and reduce function you'd like to use. The intuition is that it would be so much easier if we would just write SQL, right? On top of, instead of MapReduce. You write a SQL query and then it's just mapped to MapReduce and it takes care of figuring out the details of the map function, the reduce function. This is what we are trying to achieve, basically, to use MapReduce as a low-level layer, but on top of that, we want a layer that has an actual language. So a first effort, even though it doesn't go all the way to SQL, was called Apache Pig. This is the logo of Apache Pig. It's basically some sort of language that doesn't require you to write the map function and the reduce function in Java or have to deal with all that code. So you just need to write a few lines like this, high level, that more or less corresponds to a MapReduce job. And the simplest one have exactly these 5 parts. You load the data, which might also infer some columns and so on. That's already a high-level mechanism of Apache Pig, that it might read, for example, a CSV file. Then you have your map phase right here, where you filter, right? Where you're saying, but it's on a high level, there's no key value in there, right? You're already on a higher level than the processing level of MapReduce. You just have your database records from the CSV file. You say what you want to do. So in that case, filter, that could be a map function, right? To filter. Then that's shuffling. You basically say by what you want to shuffle. So score basically will be the key in MapReduce, the intermediate key. So that's going to shuffle grouping by score. And then that's your reduce function, which is basically going to aggregate the score is the key and count is the aggregate. And finally, you give the output. Dump is just putting it in your screen, but there's also store that would store it back to S3. So you see, this is basically an MapReduce made easy, right? So this is Apache Pig. Who is with me? Right? So that was one of the early frameworks that made it a bit more convenient to use. Now I have a feel-good slide. Do you remember that 2 weeks ago I showed you the data models with the atomic types and the integer, string, structured types and so on? Who remembers that lesson? Now I'm going to show you one slide and I want everybody to raise your hand if you think it's going to be a walk in the park to be using the data types of Apache Pig, based on the lecture I gave you 2 weeks ago. Who thinks it's a walk in the park? I see many raised hands already, right? It's all known territory. What do we have? You see, we have int, long, these are integers, float, double, we saw them. These are strings, char array, these are sequences of bytes, hex binary, base 64 binary in JSONic, date times, big integers that would be a long, or no, even more than a long, that's actually integer, like the entire space. Here, that's any decimal. Complex types tuples, these are JSON objects. Sorry, these are JSON arrays. Sorry, that's an ordered list. Tuples. We have maps. These are the JSON objects. And what they called bags, these are actually the tables. It's basically a collection of tuples, which is essentially a data frame or a relational table. So you see, everything you see here, it might be using different names and not be the exact same list, but that in principle is very easy to learn because you already have the generic matrix, the generic knowledge to understand these things, right? So this is what I wanted to show you. I don't ask you to learn that. I just wanted to see that there's nothing surprising in there. And my goal is that whenever you look at a framework like that, you see just with a cursory look, you open the documentation and you should have the immediate reaction, aha, this is familiar, right? I just need to figure out the names, but that's it. That's familiar, a familiar looking list of types. That's how I would like to make you feel so that you can very quickly figure it out with any new technology you use. But people went further than that, and I mentioned it already last week. People went ahead and even implemented SQL on top of MapReduce, and this is what Apache Hive is doing. You can write SQL, and it's going to do it in MapReduce. That should be intuitive to you because I showed you the implementation of selection and projection already with just the map. Now you can probably imagine that group by can be done with the shuffling, right? If you group by, you just put it in the key, and the shuffling is going to produce the desired effects, and the reduce will do your aggregation, the group by. For whom is that natural, right? And the order by, that's the advanced engineering that I told you about. If you want to do an order by, then the engineers of Apache Hive figured out the fine-tuning of MapReduce to basically bring it in the desired order, right? They did it so that nobody else has to do it again. Then everybody else just types SQL and that's it. That's the intuition. So you should see MapReduce as some intermediate layer that we have in the big data stack. And then on top of it, we can build some more abstract levels with Apache Pig. It's called Pig Latin, by the way, the language here. It's called Pig Latin or SQL or other languages. So that's what I wanted to show you. So now let's see, before I start a bit on Spark, how much of that you actually understood. Do I need to press anywhere? No, it should just here, yes. So hopefully what we've learned during HBase and that we could reuse in here should give you a high-level picture of that, right? So we have a majority in 80 to 99%. Some people understood everything. A few of you maybe a bit less, all right? So my recommendation, so first you should read the textbook and you should use it in practice. Try to run a few MapReduce jobs, try to write a few map functions, reduce function, combine function, try to implement an average reduce and to come up with a combined function and key value layouts for the intermediate pairs that is able to push down the pre-aggregation of the average, which is a very good exercise. And of course, you can ask questions. So if you didn't understand, especially those who are less than half, if there's any area that you don't understand, send me an email, send the TAs an email, come to the exercise session, ask questions, put a question on the Moodle forum, ask your friends, because if they try to explain it to you, that will also make them learn even more. So do not hesitate to communicate. There are plenty of people here that can explain and help for those of you who have questions. Okay? Any question to conclude, or should I move on to Spark? Yes, over there, if we can bring.
Thank you. And if every, oh, I hope I get the terminology right. If every node that's running a map task, if they
map
can.
Plot? Every map slot?
Yes, I think so. So if they can just dynamically create any intermediate key they want to, how do I know which reduced tasks exist and which reduced tasks need to be assigned?
So basically as the user, you need to think on the logical level. You need to think of the map function and reduce function as logical, right? Without worrying about the tasks. The tasks are an implementation detail that batches the execution. You just need to think with the logical walkthrough. If you run your map function and reduce function through the logical walkthrough, do they do what you want to do? The rest is figured out by MapReduce. MapReduce has this default behavior. It will hash the key values to put them in the right batches for the reducing. But you as a user shouldn't have to worry about these details. Only if you're an advanced user and you care about sorting and so on or want to fine tune.
Okay, so the user doesn't have to specify which keys are created during the mapping phase on his own.
You do need to define your keys because when you write your map function, you have this call that generates an intermediate key and an intermediate values. So you will generate intermediate keys. MapReduce guarantees you that these intermediate keys that you generate will all be grouped key by key. So that it guarantees you that, and it guarantees you that all the key values coming from all the map tasks that have the same key will be together during the reduce phase. That's what it guarantees you. How exactly the keys will be hashed and distributed over the machines is a physical detail that shouldn't change the correctness of your implementation.
Okay,
Right?
thanks.
Okay, thank you. Any more questions? Otherwise, I'll start with Spark. Okay, so let me stop the recording here.